Hello and welcome back. Now we're going to go through an example illustrating how the flip-flop equations are used to calculate clock period and if hold times are being violated. Then we're going to look at CMOS transistors and how they relate to the delay of standard cells and why we end up with multiple standard cells to meet various delay requirements within the library. And then we're going to look at how the designer determines clock period through the details of the design, and how concepts such as pipelining and micro-level parallelism can be used to enhance the performance of a design. So here's a simple example with two flip-flops, two NOR gates in between. On the right-hand side are given the minimum, typical, and maximum delay for each of the delayed elements. This is a Verilog format. What I'd like you to do is to pause this for a moment, calculate what is the delay of the critical path, and thus through the equations given, what is the fastest possible clock frequency for this design? And secondly, is there a potential for a hold violation? Okay, you've done that. Let's go and see if your answers are accurate. So we apply the equation that we derived for the minimum clock period for a flip-flop based design. That is, the clock period has to be greater than or equal to the maximum clock to Q, the longest delay on the longest logic chain, plus the setup time plus the skew. Note, the longest logic chain is through these two NOR gates. It's not through just one single NOR gate. And thus the delay associated with that is 6 nanoseconds, 2 times 3 nanoseconds. Next, we apply the inequality that was given to determine if we have hold violations or not, and see if we have hold violations. So we'll look that up. The inequality that has to be met to make sure there's no hold violations is that the sum of the hold time plus the clock skew has to be less than or equal to the minimum delay through the logic, that is T clock to Q min plus T logic min. So we calculate those using the values that are given. Hold time is 2 nanoseconds, the skew is 1. T clock to Q min is 3 nanoseconds. And T logic min is the minimum delay through the shortest logic path, which is this NOR gate here. And that minimum delay is 1 nanosecond. Do we have a hold violation or not? The constraint is satisfied, so no, we don't have a hold violation. What would we do if we did have a hold violation? Or more precisely, what will the tools do if we had a hold violation? The tools would insert additional logic into the shortest logic chain, even if they're just buffers, in order to increase the delay in the shortest path through the design. Next, we'll look at how the delay is related to CMOS transistor sizes and how this influences the standard cell library. You might recall a governing equation, first order equation, for the drain source current produced in a CMOS transistor as a function of the voltages at its terminals, given at the top there. The details of that don't matter so much, but notice that the transconductance depends very directly on the size of the transistor, more specifically, its width to length ratio. In the linear region, the transistor is obviously crossing linear, so the governing circuit is an RC circuit. That is, this transistor is behaving like a resistor and is driving a capacitive load off the appropriate terminal of the drain, in this case most probably. Thus, the delay is proportional to the on resistance of the transistor, which goes down with the increasing transistor width, and of course the load that's driving. So what does a circuit do if it has to drive a large capacitive load, for example a large fan out or a long piece of wiring? You'll select, or more precisely the tools will select a standard cell with a larger set of transistor widths. This is actually annotated in the standard cell library with x1, x2, x3, and so on. So for example, you might see inv x1 and inv x2. Inv x2 uses twice the size of transistors as in x1. Thus it can drive a larger load in less time than in x1. And so all I'm doing here is relating a timing related parameter in terms of how cells are selected from the standard cell library in actual synthesis by the tool in order to try to help meet timing constraints. Finally, in this submodule, we're going to look at a simple design and how concepts such as micropipelining and exploiting microparallelism can lead to a faster, better design. In doing this, I'm also going to introduce the concept of FO4 as a process-related metric related to timing. FO4 stands for the delay of a minimum size inverter with a fan out of 4, that is, it's driving 4 copies of itself. That delay is measured from the input to the loaded output of that inverter at the 50% points. The value of this delay is that it is often used as a single number to represent the digital performance of a logic process, of a manufacturing process. So for example, you might be comparing two vendors' provisions to give you a 22 nanometer process. One might have an FO4 of 20 picoseconds, the other might have an FO4 of 25 picoseconds. Thus you know already that the first one is going to produce significantly faster designs than the second one. Of course, this is the only thing to consider. You have to consider power consumption and cost, but nonetheless, this is an indicator of the digital logic performance of a semiconductor process. I give an equation at the bottom here to estimate FO4 as a function of gate length, of effective gate length, and an example of that. These aren't meant to be actually accurate numbers. In fact, that number is significantly off. Unfortunately, I can't give you, of course, numbers for actual FO4s because they're highly proprietary. So what we're going to do is use FO4 as a process invariant delay factor, and then just count delay in terms of units of FO4, so we can get an idea of the overall speed of the design in a process independent fashion. And very approximately, I'm going to use these values for delays of different logic elements as given on this page. And these are only meant to be approximate. A more accurate set of numbers would have more decimal points. In addition, I'm going to assume, and this is only an assumption for the purposes of the calculations on the next few pages, that the clock skew is equivalent to 1 FO4 as well. This is only assumption. I'm not saying that in general clock skew is 1 unit of FO4 in any particular process. So what we're going to do is design a comparator. The function of this unit is to compare 4 numbers which are put into the register on the left-hand side, and tell us which is the largest, and put that in the register on the right-hand side. And the most straightforward way to build this is to just string the 3 comparators that are needed to compare the 4 numbers in series, thus creating a long critical path. In addition, and we'll come back to this point after we've looked at coding, the most straightforward way of writing the RTL code for this function would produce this design. The point I'm making is, if you want the more sophisticated designs we see on the next few pages, you actually have to think about it while you're writing the RTL. The tools won't produce them for you. So in this example, if the delay through the comparator is 10 FO4, what is the clock period using the other values required from the previous page? Well, T logic is now 30 FO4. Add in 2 FO4 for the clock to Q delay and 1 for each of the setup and skew times. We end up with a clock period of 34 FO4 for this particular example. Now the question is, what can we do to speed this up? And we're going to look at 2 techniques to speed this up: pipelining and exploiting microparallelism. Concept of pipelining you're most probably familiar with. Basic idea is to add pipeline stages so that the calculation is distributed amongst multiple stages of the pipeline, and thus each stage of the pipeline takes less time to do its operation, and the operations are happening in parallel. So this example here, we put a set of registers in between each stage of the comparator. Now the critical path is only one comparator, so the designer is operating faster. Furthermore, it will actually be doing multiple calculations in parallel. There will be a different calculation going on in each stage of the pipeline at the same time. However, we've lost something, and that is the latency through the design is now 4 clock cycles. It takes 4 clock cycles to get from the left hand of this design to the right hand of this design. So the latency mattered versus the throughput, the number of calculations you can do per second, then we wouldn't actually want to do this. So let's illustrate the operation of this design operating as a pipeline. On the first clock cycle, present that number on the left. On the second clock cycle, present the next number, and the first number has gone through the first register or pipeline stage. On the next cycle, we've done the first calculation, which appears in the output registers there. The item in blue is moved to the outputs of the first register, and we present the items in red for the next calculation. On the next clock cycle, we've done the next stage of the computation for both the items in black and the items in blue, and notice this is happening in the same time. This is the intrinsic parallelism of logic, that it can do this. It can do the calculations for 3 and 4 and A, C, and D at the same time. The items in red have moved to the output of the first register, and the item in grey is being presented for the next cycle. Do one more stage of calculation. The item in black has now completed its calculation. At the same time, we've done the next stage of the calculations for the blue set of data and for the red set of data, and the grey set of data is about to start. So you can see here, in this pipeline, as well as reducing the critical path substantially, we've increased the throughput because we're doing 3 calculations every clock cycle. Those interstage registers that just appear on the wires are very necessary. If you don't have those, you'll lose the synchronicity of the data going through the design. In the example on the previous page, notice blue stays with blue, red stays with red, black stays with black at each stage. We need these intermediate stages of registers, even though they're just going to wires, in order to keep the different colors together, or the different waves of numbers together. If we don't do that, let's see what happens. Well, first cycle, present the first number. The second cycle that goes through, present the second number. What's happened on the third cycle? The wave of data has lost its coherency. The black data has been split up. We get 2 results. We don't even know what they are because we don't have sufficient information. And the first result has lost its synchronicity. The number 2 there has lost its synchronicity with the others. Go to the second stage, this continues on. Yes, we start getting numbers, but they don't mean anything anymore. That value of 2 there was produced from 2 different waves of numbers going through the system. So we've now mixed up our trains of numbers and are not getting good results from this. And that's actually the outputs of the registers on this cycle. So we very much need those registers that are there. So let's now calculate the clock period with the pipelined example. The logic path is now only 10 FO4, so the clock period is now 14 FO4. So the delay improvement is 2.4x, and note it's not 3x because of the setup, clock to queue, and skew associated with the clocked elements, the flip-flops. Notice also we've increased the area. So if we can't actually utilize this structure, if we can't keep the pipeline full, we actually end up being worse off than in the previous example. But if we can keep the pipeline full, that is, a new set of numbers arriving each clock cycle, we've improved the performance per unit area quite substantially over the first example, over the first way of doing this. And one point I want to make on this particular slide is that the code, the RTL code for this structure, this logic structure, is very different than the RTL code for the original design. The way you code it represents a data structure style and gives you quite different results depending on how you do the coding. And we'll see that in a later set of notes. Another way to speed this up is to recognize that you can do things in parallel at the logic level and thus shorten the critical path. And that's what I'm illustrating here. So here I've just I realize I can do the comparisons of the first two numbers and the second two numbers, numbers 3 and 4, at the same time. Then present the results to another comparator to get the final result. I've reduced the critical path, actually at the expense of no more logic. This is the same amount of logic as the first example. However, it's also coded differently. Again, the most straightforward way of writing this code would not produce this design. Now the clock period is 24 FO4. We have no increase in area, and we have an increase in performance per unit area. And again, we're going to see how different the coding is for these three examples in a later set of notes. Finally, I want to introduce you to the concept of retiming. This is conceptually a simple concept in that if you have a critical path that's determining your clock period and you want to make the design overall faster, you sometimes have the opportunity, particularly in a pipeline structure, to move logic to a different stage of the micropipeline. So for example, at the top there, I've got two combinational logic blocks with those two different delays of 20 FO4 and 5 FO4 in the first stage of the micropipeline. And I've only got 10 FO4 in the second stage of the micropipeline. Thus, the clock period is determined by the critical path in the first stage, which is 29 FO4. If it makes logical sense to move the combinational logic block with a delay of 5 FO4 to the second stage of the pipeline, if it makes logical sense to do that, and that's very design specific, then I can reduce the critical path to 24 FO4, a significant improvement in clock cycle performance. But notice the details of what's happening in each stage of the logic pipeline has changed. You've postponed some of the internal calculations by one clock cycle. So that brings me to the end of this particular submodule. Remind you some key points. We used FO4, which is the delay of an inverter with a fan out of 4. It characterizes process performance. And by the way, you can get min FO4 and max FO4 from the process. So it also gives you an idea what the process variation is. And I've used these to illustrate delay estimates. And I'm particularly reminding you here that the beauty of logic over code, over computer code, over software, is that you have a lot of microparallelism available to you. Within your design, every chain of logic between every pair of registers is operating at the same time. And if you want high performance logic, you have to exploit this high level of microparallelism. And I showed you some different ways of doing this, adding pipeline stages, rearranging the logic so it's more parallel rather than serial, and retiming, all effective techniques to reduce the clock period. Now what I'd like you to do is to take the submodule quiz for this particular submodule, and after you've done that, proceed to the next video submodule.